Happy Friday, everyone. Happy to see so many people here, given that class isn't usually scheduled on Friday. Was worried about people forgetting. Before we get into stuff, I wanted to give a correction for the example from last time. We went through a bunch of pretty cursed array examples, and we found that all of them were equal, or all of them were equivalent, except some of them are not. In particular, this one, where I messed with the brackets, that turned into just the memory location denoted by array, then take the value at that memory location and add 2. Since we had 0 at index 0 and 2 at index 2, this ended up just computing 0 plus 2 instead of getting the 2 that we wanted to get. So, lesson learned, I'm not going to assign values that are identical to array indices. Cool. This one still works, though. So, that array example wasn't meant to take up the entire class, but it's kind of a nice coincidence because now we're just only slightly ahead of schedule instead of way ahead of schedule. I still hope to be a little bit ahead of the planned lecture schedule in order to have dedicated work sessions closer to the assignment due date, but right now we're half a lecture ahead. When we left off, it was with this bullet point. Let's write code that crashes in Java and C. So let's do that. I logged out so that anyone coding along has time to log back in. Totally didn't do it accidentally. Shout out to SSH keys yet again. So we should probably be used to this by now. I'm going to change directory into my comp2160 folder. Press tab to complete it because instructor is a pain to type. We're going to make a new directory for the crash example. Mkdir. CD into that. And we'll be able to get going. The first example that I wanted to go through is a bit pedestrian. We sort of went through this with the silly array example last time, but I'm going to just go through it quickly for completeness. Pay attention here, we're using Java this time. And of course I used I to get into insert mode, and I'm typing the classic Java boilerplate. And now several words in, I'm actually writing some code. I'm going to define an array. And that's it. Escape to enter, or escape to exit insert mode, colon for commands, write, quit. Easy. And then we're going to compile it using the Java command line tools we talked about earlier. Oh no! What did we do? Index 6 out of bounds for length 5. Cool. I know I've been talking all about how funny and dangerous arrays are, but this is just a reminder of the safety features that exist in pretty much every other language. So now we're going to try the same thing in C. I for insert, C boilerplate. And remember, inserting variables into strings in C works differently, and we do %d as a placeholder for a decimal number, \n for a new line. Then we're going to not forget the exit code. And before we see what this does, which should be a bit predictable given yesterday's examples, I wanted to talk a bit more about exit codes and portability, because you might remember in yesterday's example, one student had a question about the practice of returning 0 at the end of a C program, and I removed the return 0 line to see what would happen, and nothing happened. It still returned 0. It just happened to work. So that means you don't have to return 0, right? Well, I later tried it out on my local machine, coincidentally, while also identifying that coincidence that I pointed out earlier. And check that out, 255. So what does that mean? I don't know, it's meaningless. There just happened to be a value 255 at the memory location where the return value is supposed to be. And my shell displays this in red because the convention is that if a program returns anything other than 0, something went wrong. And this specifically is basically telling you that you should Google serious arrays example exit code 255 and do some troubleshooting. So what I'm pointing out isn't really about exit codes, but is about portability. C can work differently on different computers because the compiler is implemented in a slightly different way, and undefined behavior comes into effect where the C specification just doesn't say what should happen when a return statement is missing. So behavior gets unpredictable. Other moral of the story, test on Aviary. The markers are only using Aviary, and if it works on my machine, they won't care. They're very mean. So then we're going to compile it with Clang. Oh, there we go. Clang warning all. -O for output. Undeclared identifier. Oh, I must have forgotten an include statement. So using the magic of Vim, I'm going to insert on a new line using capital O and put the thing that I forgot. This should work now. I'm using up on the arrow keys to access previous commands. Okay, and it's just giving us warnings that we're going to gleefully ignore. And it keeps working. It went right past that illegal indexing, no problem. So now we're going to go a bit further with that because that's basically what we did last lecture. Now I'm going to do lowercase o to insert on a new line below the cursor. Press enter again for aesthetics. And we're going to start looking at strings. After this example, we'll talk more about strings actually in the lecture. But check this out. You'd think that to define a string in C, I would type, I don't know, string. String. Cool. Spoiler alert, this won't compile because strings don't actually exist in C. They are just a convenient abstraction for an array of char, and that will cause a lot of problems for you. So we're going to go back. I used escape to exit insert mode, and I'm pressing B to go back one word a bunch of times. Now I'm going to press CW to replace one word and type char and define an array. So this line will work, but I'm going to be saying again and again, strings aren't objects. I guess saying strings don't exist was a bit of an exaggeration, but they are definitely not objects. This line is just a convenient shorthand for basically saying char string of however many characters are in hello world. String 0 equals H, string 1 equals E, string 2 equals L, and so on. So say we want to change this to uppercase or something, a common operation on Java strings. We might think we want to call a method. This won't work either. Are we going to get a compiler error or a runtime error? Probably compiler. I'm going to go up through my command history. Member reference base type char13 is not a structure or union. Nice error message. That would be pretty incomprehensible if you were trying to work with strings as objects, but luckily you're listening to this now and you will never do that. So what's up with strings? I think we're about to find out. Oh, and must mention, you will grow to hate the word segmentation fault. You'll learn to hate them a tiny bit less when you learn about debugging, but you will still hate them very much. I even got a shiver down my spine once this thing appeared on the slides. Strings, they're not objects. Strings in C are just dumb arrays of char. And as I've said over and over again, or not exactly said, talked about over and over again through the last couple lectures, arrays in C are very dumb. So this is like 2 layers of dumb. They don't have any methods or properties, so no dot length, for instance, because they are just dumb arrays of char. Strings are not immutable, like in Java. You can change individual values in arrays, thus you can change individual letters in a string, because strings are just dumb arrays of char. Strings cannot be assigned like they can in Java. We are able to assign the value hello world to that string on initialization, but you can't do that again. You get a memory location of the array, and you're stuck with that because they are just dumb arrays of char. Strings can be declared as arrays or as pointers, which are actually the same thing, but actually not. We're going to look at pointers later in the course. But of course, why is this? Because they're dumb arrays of char? Aw, that joke isn't on that last point. So let's go back to the terminal and write some more code to work with strings. Hopefully you're still logged into Aviary. Where are we? Going to print my working directory. Crash example. Okay, so let's make a new directory in the comp2160 instructor folder. cd ... for the previous directory. Make dir string example. I'm going to make this strings example. And then we cd into this. Pretty simple stuff. Vim strings.c. And we're rolling. We include the standard I/O, as well as the standard library, because I'm probably going to end up using that return exit success thing. Another distraction. I just remembered that a student last class asked me if the text editor you use affects the file that you create. Like, say, is there a different compilation process for Vim versus Nano or something like that? The answer is no. A C file is a C file. Use whatever text editor you want. Usual entry point, a function that returns an int and takes no parameters. We're going to declare a string as an array. Did I put an underscore there? That meant to be a space. Doesn't matter. Also notice that I didn't have to specify the size of the array. The C compiler will figure out the intended size based on the length of the string, and then add a special character to denote the end of the string, which we're about to see in action. So let's print our string. So this, I believe, will maybe work, but the compiler won't like it. So let's just wrap up this program and see what the compiler has to say about it. Clang, all warnings, strings.c, turn that into strings. Also, I want to share a bit of a horror story and motivate you all to type very carefully. If you type strings.c as the output file, as I did once, you know what'll happen? I'm just going to copy strings.c into strings backup. By the way, I canceled that command using Control-C. ls. Oh, I forgot the .c extension, but whatever. This example will still work, and I'll be able to recover my work. Hello? Huh. That wasn't me, was it? I'm going to turn my volume all the way down just in case. Okay, so, I forgot all about that printf thing. So format strings not string literal, potentially insecure. Cool. I don't know the exact mechanics of it, but it must be that if you send a string directly to printf, that can probably open you up for some data corruption issues, potentially similar to what we talked about with accessing arrays out of bounds. So then we can just run strings Oh, right. The executable is called strings.c. Okay, so it printed daily life just fine, but we should still trust the warning. I don't know what might go wrong if you do this, but the C compiler developers know a lot better than you or me, so we're going to follow that. So let's go back into Vim. Whoa! Ubuntu? I don't remember writing 2 lines of ats and carets. We're looking at binary code. And yeah, this is the cautionary tale I wanted to tell. When we ran Clang with the output argument that is named the same thing as the input, it overwrote the input without a second thought. And if it were, I was going to say 11:50, but the due dates are mean. If it were 3:50 p.m. on the due date, and this happened, I would be screwed. So use a backup. Even better, use source control. Don't be like this command. Luckily, I had a backup. Going to delete strings.c since it's now useless. And rename strings backup back into strings.c, and we should be back in action. Phew, I've never been so happy to see a short mainline in my life. So we're going to just fix this error. The placeholder for strings in C is %s. You don't need to memorize this. Actually, you will end up memorizing it because you're going to write it a lot, but you don't technically have to. And then we saw earlier that doing string.length did nothing. Crap, made the compiler refuse to work, in fact. So how do we find the length of a string? So in lieu of being able to use dot notation on objects in C, not objects, on whatever in C, we call functions that take those objects as arguments. And the function to calculate the length of a string in C is strlen. Cool. And then just to prevent that error from popping up again, we'll make a short string with a placeholder. We're using %LU, which I believe stands for long unsigned. This is just to go with the exact data type that strlen returns, but I'm sure that using %D as before will also work. Actually, let's test that. Oh, that was my bad command. Phew. Okay, so this was a mistake. This is something that I actually wanted to explore and demonstrate. So format specifies type int, but the argument has type unsigned long. I'm going to just go back to that helpful Wikipedia article. Unsigned long? Cool. 32-bit integer. But we gave it this format specifier for int, which is 16? Yeah. So as long as the return value that Sterling gave us is within the possible range for an int, it'll be fine. So this is kind of an impractical example, but it shows a concept that'll be applicable in other situations. If your string is at most 32,767 characters long, you'll be fine. But unsigned long can take up represent way larger numbers than that. So if it's more than 32,000, I don't know what'll happen. More undefined behavior. The compiler can do whatever it wants with it. It will most likely overflow and show a value that is way shorter than you expect. But it can do whatever. It could crash your PC. It could send a mean email to your professor. It could do whatever. Always be on the lookout for undefined behavior. Oh, and that Sterling is because I forgot to say include string.h. Wah, wah. So lowercase o to insert on a new line, include string.h. Fixing the format specifier.
I had a question about that.
What's that?
So does it not care about like leaving zeros then?
Leaving zeros.
Like it's sending a 32-bit value back, but like there'll be a bunch of leaving zeros. It'll still fit into that 16-bit framework.
Okay, so
I guess I'm saying if it sends 30,000, there'll still be a bunch of zeros in 32 bits. You see what I'm saying?
yeah, so indeed that 32,000 when represented as an unsigned long will be a whole bunch of leading zeros and then 16 ones. So would that actually cause it not to cause any issues? Let me think about that. This will still be bad because we're going from an unsigned long to an int. If we were going the other way around, it would be fine because we're just taking a smaller value and giving it more space. But taking the unsigned long and potentially just chopping off half of its bits or making it overflow, that's what would cause issues. Does that answer your question?
Yeah.
Cool. Yeah, I guess I was wrong about the overflow thing. It wouldn't overflow, but instead it would just be, most likely be truncated, which means that the first 16 bits of the unsigned long would just go, and then it would return, or it would show whatever number the remaining 16 bits represent. Of course, since it's undefined behavior, my initial explanation might have been correct for some C compiler. There are no guarantees. Okay, so this should work as intended.
A quick formatting question.
What's up?
I noticed when you were writing like in Java, like you had like the open little bracket on the same line.
Oh, yeah.
On C, whenever you do C, you like put it on a new line and leave a gap. Is that just like a C thing?
Yeah, if I talk too much about it, this class will turn into arguments about brace placement 2160. And so I'm not going to touch that. It's a C thing. So we're going to compile it again, run it again. Daily life 10. That right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Excellent. Let's move on. So I wouldn't blame you for thinking that, yeah, this looks awesome. Sterling just works. But hopefully a couple of you are scratching your heads right now. We talked a couple days ago, feels like a millennium ago, about how arrays in C don't know their own length. So if C strings are just dumb arrays of char, then how are we able to get the length of it? That's because strings actually have an extra character at the end to denote the end of a string. So our array looks like D, A, Y, L, Y, space, so on, F, E, end of string character. Whoa. So Sterling is able to tell how long the string is by starting at the beginning of the string and counting elements until it gets to that end of string character. We can abuse this. So what does the end of string character look like? Looks like this. \0. This is a special value that is equal to 0. Each letter has an ASCII code that means that it is represented by some number. This is 0. So now our array will look like D at index 0, A at 1, I, L, Y. Okay. Again, I'm a theoretician. I can't count. But if I'm correct, there should be an end of string character at index 4 overriding the Y. So let's print out the string again and see what happens. Actually, I'm so much better than this. I'm going to copy and paste. How do you copy and paste in Vim, you ask? Going to do capital V for visual line mode. Select both of these lines by moving the cursor. And then Y to yank, copy. Go down here, and P to paste. Very difficult to predict where the white space will be, so I'll just fix that up. And as another convenience, let's just put a new line in between the two sets of output. Compile, run. The string is now Dale and has length 4. The rest of the string still exists in memory, but Sterling and pretty much every function that cares about the length of a string will ignore it because, well, there's nothing really separating the end of an array from the rest of memory, so we need that end of string character to be able to tell. What's that?
That's a quick question. After the playing line, what does the dot backslash before strings do?
Good question. The dot represents the current folder, and then slash just to access a file within that folder. We specify that the executable is inside of this folder because sometimes, if we don't, not always, but sometimes, the shell will get really confused thinking that you're trying to access a built-in command called strings, but there isn't one. So I bet it'll still work if I do this. Yeah.
So that works because you're in the same directory, right?
Yeah. Yeah, actually, from another directory, we can still run the executable by providing the correct path. Yeah. So this worked. It's probably an aviary thing. Sorry, this worked and is probably an aviary thing set up so that it always works correctly. But occasionally it'll just give you an error saying that it's not a built-in command, even if you're in the correct directory. So put this // to indicate the current folder just in case. That way it'll always work. Question?
I used the pointer to make the string.
Uh,
I got a segmentation fault.
Good job. May I see it?
I used it now,
Oh, wait, if you change it, then I won't take a look. We'll look at defining strings as pointers later. So without being able to see the code, I would guess that there's some sort of, maybe a bounds checking error, because even though I've been talking all about how C doesn't do bounds checking, the operating system does do some bounds checking. And if you tried, I don't know, allocating space for your array, oh, you probably need dynamic memory allocation to define the string as a pointer, which we haven't talked about yet. So yeah, your segmentation fault happened because you haven't learned about the thing required to not have a segmentation fault. Huh? Oh, did I actually do that thing? No. Oh. Actually, there will be no strings exam, don't worry. I'll just demonstrate that Vim and pretty much anything else that takes a file path. So just like we are able to execute strings by going into the strings example folder, we can also give Vim a file that is in another folder. Just need to specify it. Okay.
So I'll just ask, is the formatting a / like another directory or layer deeper?
Sorry, what were you asking about?
Like when you go bin strings _ example, is that / between example strings like a directory deeper?
Yeah. I should note that this is a /. It's weird naming because you'd think it would talk about the direction it goes from top to bottom, but no, it's bottom to top. This is a /. And yeah, you're correct. We're denoting strings example, go into that directory, strings.c. This notation is consistent with paths throughout the system, like you can see here. What's that?
Can you use casting just like we did in Java?
Casting?
Yeah, like
Ooh.
you can cast a line into int instead of just remembering the formatting range.
Oh, okay. The answer is most likely yes, but I'm going to test that. So you're asking if this is okay to do? So I think that it's good, and that the compiler was warning about an implicit cast. If you write this, then you might not be aware that a cast is happening, and so the compiler is polite enough to warn you about it. But if you write this, you have explicitly said, yes, I want the value returned by strlen first to become an int. I know what I'm doing. I promise. I'm a good programmer. So I don't think we'll get a warning, but let's see what happens. Oh my gosh. Actually, I'm just going to go into the right directory and type commands. strings, not .c. Yeah, compile it without issue because we specified that we want to cast that unsigned long into an int and basically said, I don't care about those first 16 bits and I'm prepared to deal with the consequences of losing them. What's also what?
And to pass as a character array in a function, right? We need to pass it as a pointer. How are we supposed to do that question one? Because there are multiple functions there.
Wait, I'm just going to go back into the code and ask you to answer that again. Okay, can you ask it again?
Yeah, to pass the string in a function, right? We use
Yeah.
pointers.
So, like we do with Sterling?
No, we use pointers, right? For example, I want to make my own function,
Mm-hmm.
and we use pointers for that, right? If you want to pass a character array or a string.
Okay, yeah.
So how are we supposed to do that when we don't know how to benefit pointers in the sign?
Okay. I think I understand what you're saying, and that the answer to that is that we can cast pointers to different types. So just as I casted this unsigned long into an int, I was able to, I would also be able to cast, say, an int pointer into an unsigned long pointer. Is that what you're asking about?
Are you talking about a method declaration line?
Yeah, kind of. Like when we declare a method, right, we use pointers instead of the sort of character array. For example, I want to declare a method that is int, strings, bracket, char, pointer string.
Oh, like in the Java boilerplate?
Yeah.
Let me just go back to that. Okay, so we have something like this string array, and then continue.
Similarly, when we are doing the same, when we are initializing our function, right, declaring a function, if we want to input the parameters, can we pass that array as well, or we need to pass in pointer?
Okay. So I think the real answer to your question is that they're the same. I'm going to go back into the C code. And wait, are you asking about C or Java? Okay. So you're wondering, if we were to define a function that takes a string, do we just pass in, or do we specify that we want a char array, or do we specify that we want a pointer?
Yeah.
Okay. Glad I finally got the question. Yeah, do whatever you want. They're the same thing.
When I pass just the array, right? Instead of pointer. So will it immute it? Will it change it to the function, right?
It wouldn't change the design of the function. Like, we'll see later that arrays essentially are pointers, just a pointer to the 0th element of the array. So you can indeed use pointers like you would arrays. You can even use array indexing on a pointer, because as we saw last class, array indexing is just pointer arithmetic. So yeah, there are syntactical differences, but they're ultimately very small, and you can use arrays and pointers in basically the same way. Is that all good? Cool. Then did you have a question?
No, I think what he was confused was the header declaration as a pointer, as a car pointer. So he was confused how he would pass a string to that function, because the function declaration as a pointer.
Which function declaration?
Like, for example, if you declare a function Sterling early, and
Oh, okay.
Sterling inside of the function header, you would have a car asterisk and then that, right? So that
Okay.
looks like a pointer.
Yes. In fact, let me see if Sterling has a man page.
Yeah.
Yeah, so something like that
Yeah.
does look a bit weird, but the answer I ended up giving still applies. Arrays and pointers, while not the exact same thing, act so close to each other that you can pass that char array to where it specifies a pointer and you'll have no problem. So what are we supposed to do next? Let's try some illegal indexing. So we're making a placeholder for a string within our string. And let's see, actually let's do some normal indexing first. We'll get silly very soon. First, 0. This will print out the first letter of the string. Pretty easy stuff. What's that going to do? Yeah. Undefined behavior. Let's see what this specific compiler has in store for us. Ooh. Oh, messed up the formatting, format specifiers. I'm going to run it anyway because it may or may not still work. Segmentation fault. Woo! So what happened here? So this printf was expecting a string, which is actually an array, which is actually a pointer, but we gave it the first value of first, which is a string, which is actually an array, d. And out of curiosity, I wonder what integer value d corresponds to. Lowercase d specifically. 100 in decimal or 64 in hex. Yeah, power of 2, nice. What's at address 64? I guess this might not seem like such a weird number to you at this point in the course, but once you start working with pointers, you'll see that pointers are usually way larger numbers than 64. I think like 16 hex digits or something. I don't really know. You don't need to know exactly how long pointers are, but they're long. So at address 64 in the computer's entire memory map, that's probably like boot time initialization code for your operating system. So if we were on a less capable system, it would have just done whatever. But the operating system does have its own safety features, even though the C program we're running itself doesn't. And it sees us trying to access such an early memory address and says, nuh-uh, no way, you're not doing that. That was fun. So let's fix the formatting specifier and then see what our array indexing printfs actually print. So the warnings were on line 20 and 21. I'm going to press colon to go into command mode and just type 20, enter. I jump to line 20. Nice. I believe it was %C for a char. And let's try this again. Giving us that out of bounds warning, but we're all good. D. And then I guess our indexing of first at index -2 showed something. It could be a coincidence that the value that happened to be in memory was 32, which is a hex code for a space. But it's much more likely that it was just some random value that doesn't correspond to any char. Now I'm using the brackets to skip between new lines. And lastly, for this example, we're going to check out, well, we're going to follow up on this little weirdness because, as we saw earlier, inserting the end of string character into the string basically had the effect of shortening the strings. But the characters after the end of string character still exist, and I'm just going to access one of them. So we replaced first at 4 with the end of string character. 0, 1, 2, 3, 4. 5 would give us a space, which isn't very interesting. So let's check out index 6. L, but it's not an L. This is W because we are able to access characters that were beyond the end of the string. So that's all for this example. Hopefully I've made it super duper clear that strings in C are just arrays. Arrays are dumb. And by the transitive property, strings are dumb. Now let's talk about functions, which are pretty similar to methods in Java, but have a few important differences, most of which stem from the fact that C is not object-oriented. So they have a return type, or void if you're returning nothing. They have a name. They declare parameters with types and names. But there's a silly difference that is actually a holdover from memory limitations in the olden days of the first C compilers. They need to be forward declared, which means that a declaration or definition of a function must be in the code before you call that function. Does it ever tell you to code along? I'm going to do an example of this. So I'm going to cd back into the previous directory, make a directory for functions example, cd into this, and then let's make silly function.c. I'm going to speed through that C boilerplate. And this code will just consist of a single function call. If we ran this now, it would complain about cool function not existing, but that's not important. What is important is what I want to show you about the order of things in C code. Oops, forgot the return type of void. And we'll just make this print hello world. So this looks like a perfectly cool and chill program, but it's not. Cool function is not cool. And we're about to see why. All warnings. Silly function dot C dash O silly function. Uh-oh. Implicit declaration of function cool function is invalid in C99. Ah, wait, conflicting types. Okay, that's a bit silly. This is a consequence of the previous warning. We didn't specify a return type when calling cool function, so the compiler gets mad at us because that technically conflicts with the declaration that this will return nothing. And then this warning was due to me forgetting stdio, so we'll fix that. Oops. So how do we fix this? One option is to declare the definition before its definition. Declare the function before its definition. And we do that by specifying the function signature in much the same way as we did at the start of the function. Before I do so, though, I'm just going to make it take a parameter just so I can demonstrate the syntax with that. So let's say it accepts an int, and it'll print that int. Weird way to say hello to the world, but whatever, it's a contrived example. So how do we declare it? Basically copy the function's first line. And this will fix our problem. Oh, I forgot to give it a number. Yeah. I think 64 is a pretty cool number. We saw it earlier. Yay. And then there's another way to get around C's insistence that a function's declaration must come before its use. So I'm going to delete that line using dd and just put the entire declaration, or the entire function, before the main line. I'm going to select stuff with Vim by pressing capital V, down, down, down to select the whole thing. D for delete, to cut. Pretty sure these things were specified before copy and paste were even invented. And then P to paste. This will work too. exact same output. I kept saying at the start of this course that this course isn't about C, but all these lessons were kind of about C. I promise we're going somewhere with this. I was hoping to keep undoing until we got that declaration before definition, but you'll just have to imagine that declaration of the function signature. This hints at a pretty important concept in programming in general, which is the separation between interface and implementation. If you're writing a library or something, like, I don't know, SDL is a cool example of a library, lots of functionality for game developers. And you have, I'm just going to recreate the previous version of the file. And you have a function in your library called cool function. Your users don't care about the definition. They only care what parameters it takes and what it returns. Yes?
That's why this is how you should do it, right?
Yeah.
Opposed to how it was before.
Wait, are you asking, is this the correct way, or is that the correct way?
So is that the incorrect way? And the other way is the correct way?
This is kind of like bracket placement. We can argue for hours about this. I would recommend this way for reasons to do with separating interface from implementation, which will take a while to explain, like honestly, multiple classes. But for now, you could just trust me, this is a good idea. But there's nothing super duper wrong about putting the definitions before the main line. I've seen sample solutions for assignments in these courses that do it that way. I don't want to say do whatever you want, because the programming standards that the strict and mean markers are following might specify that you need to do it this way. But at the end of the day, it's not too huge a difference. They also work identically. So where was I? Interface versus implementation. Your users will only care what your function takes as parameters and returns and whatever side effects it has. They don't care about how it works. And as you go into the real world and start messing with bigger and bigger software, you'll find that you don't want to understand how your entire code base works. You just want to know how the different parts of your code base take information and give you information back. So this is our first example of separating the interface, which is how you use the function, from something's implementation, which is how it works. This isn't a very good example of it because it's just one-line function in a program that we already have complete control over. But this will come up later in the course and throughout your lives in much more meaningful ways. So, yeah, I think we're done. We don't have to worry about that exact block of code. We strayed from it big time to create that one-liner printing function, but this little block has the exact same ideas. We have the declaration here, a main line that uses the function here, and the definition here. And that's all for today. So the learning outcomes that we covered in this lecture and also 2 lectures ago when I started the slide deck and got distracted by the array example should be able to recognize potentially risky programming techniques and how they differ in different high-level programming languages. So remember some of those party tricks we saw with C arrays and how languages like Java stop you from doing that. Compare and contrast C and Java. Declare, initialize, and use arrays in a C program idiomatically and safely. Ooh, maybe I didn't quite teach that one. I told you all about how to use them unsafely. I think we'll take a look at how you might manually do bounds checking in a later lecture, but it's pretty easy to imagine just before you access an array at a certain index, verify something like if index is less than the array length, then do the thing, else give an error. Declare and use user-defined functions in a C program. That's what we just did with that example. And this is something we didn't do, hence the unchecked box. And it's sort of a sneak peek at the next lecture. Explain how C source code is compiled into machine code. So that's it. Happy Friday. Enjoy the next 8 minutes. You get them for free. And have a great weekend, everyone.